Hello everyone, welcome to the post-contest discussion for Leetcode Weekly 429. I hope you had a good contest. So let's start with the first problem. The first problem said minimum number of operations to make elements in array distinct. Basically in this problem you are given an array nums and you have to ensure that after performing some operations, all the elements in the array are distinct. To achieve this, you can perform the following operation. In one operation, you remove the first three elements of the array. And if the array has less than three elements, you remove all the remaining elements in the array. Now, an empty array is considered to have distinct elements, and after performing any number of operations, you need to have all the remaining elements in the array should be distinct. So you needed to return what is the minimum number of operations you need to make all the elements in array distinct. So let's consider the first test case, which is 1, 2, 3, 4, 2, 3, 3, 5, 7. So let's start with problem 1. Now, in this array, you could actually see that there are two duplicates. Like now you could see that 3 repeats itself twice. So this array is indistinct, and also 2 repeat itself twice. So this array is once again not distinct. What we can do is we can perform one operation. In one operation, you can remove the first 3 elements. So the first 3 elements, that is 1, 2, 3, will be removed, and our array would look like 4, 2, 3, 3, 5, and 7. Okay. Now the two duplicates, like we had two twos and we wanted all elements to be unique. That is one occurrence of each element at most. So the two duplicates had been removed. The duplicates of 2 has been removed, but we still have this 3 which repeats itself twice and we don't want that. So we'll perform one more operation. In this operation, we'll remove the first 3 elements. So 4, 2, 3 will be removed and our array would be 3, 5, 7. Now each element occurs at most once in this array. So 3 occurs once, 5 occurs once, and 7 occurs once. So this is a valid array. And to get to this array, you needed 1 and 2 operations. So the answer for this array will be 2. And yes, so this is the answer is 2 over here. And if you and let's look at the second test case, which is 4, 5, 6, 4, 4. So our second test case is 4, 5, 6, 4, and 4. Are all elements in this array unique? No. 4 repeats itself thrice. So this array is not all elements in this array are unique. So to do that, we perform one operation. We remove the first 3 elements and we are left with our last 2 elements, that is 4 and 4. We have removed 4, 5, 6 and using one operation. Does this array have all elements unique? No, still, because 4 occurs twice in this array. So we have to perform one more operation. Well, in one operation, we remove the first 3 elements, but there are less than 3 elements. So basically this corresponds to removing all elements and we are left with an empty array. According to the question, an empty array is a valid array. All elements are considered unique in an empty array. So this is a valid array. So we have reached a valid array, and to do that, we require 1 and 2 operation. So the answer for second test case is 2 again. And for the last test case, which is 6, 7, 8, and 9. Well, all elements are unique in this array. No elements repeats itself. So 6 occurs only once, 7 occurs only once, 8 occurs only once, and 9 occurs only once. So you don't really need to do any operations. So you need 0 operations. This array is valid by default. So those were the sample test cases. And let's move to the the intuition behind how you would solve this question. Okay. Now consider the first test case. So you had 1, 2, 3, 4, 2, 3, 3, 5, and 7. Now, after any number of operations, what's happening is if you perform X operations, that's equivalent to removing prefix of size 3x. So that's equivalent to removing a prefix of size 3x. Basically, what you can do over here is you can remove some prefix size. Now, if you can remove some prefix size, so basically after certain number of operations, you're removing some prefix and you are left with some suffix. So basically you're left with some part of array from the right. Now, which is the largest array starting from right, which is the largest suffix, which is a valid array. Okay, is 7, like if you just consider 7 by itself, is it a valid array? Yes, 7 occurs only once here. Is 5 by itself a valid array? The 5 and 7 valid array? Yes. Is 3, 5, 7 a valid array? Yes, 3, 5, and 7 occur only once. Now, when you try to include this 3 into the whole suffix, what happens is there is 3 has occurred before in this suffix already. So 3, 5, 7, and when you try to add this another 3, this 3 is a duplicate because 3 has occurred already in this suffix. So you can't add this 3. Now, no matter what you do, you need to remove this 3. You have to remove this 3. You can't include this 3. So you at least need to remove this part of the prefix. You at least need to remove 1,
Need
2,
for
2, 3. And so basically, let's just say that if I is the index of 3, you need to remove the first I plus 1 elements, assuming 0 based indexing. And this would be like your valid suffix. So the basic idea was that you start from the right. 1, 2, 3, 4, 2, 3. You start from the right. Okay. You try to include as many elements as possible in your final array. You have included 7. So you have included 7 in your array. All right. Then you try to include 5 in your array. Is it possible? Yes, it's possible. So you have included 5 in your array. You try to include 3 in your array, the final array. Is it possible? Yes, it's possible. Now you try to include another 3 in your array. Is it possible? No, it's not possible. So this is the part from where you have to basically cut off. Now the question is, how many operations do you need to remove this complete subarray? Okay, let's just say that this complete subarray has a length of len, and in like after x operations, you will remove an prefix of size 3x. So basically, you can see that you have to remove some, you have to do x number of operations such that this 3x is greater than equal to length, and you can see that you can just reduce this equation to say that x is greater than equal to length by 3. So the number of operations that you will need is actually the upper bound of this length divided by 3. For example, over here the length is 6, so you have to remove the first 6 elements in this case. The reason why is because this is the this is the last element that repeats itself in the remaining part of array. Now to remove these 6 elements, you would have to do 6 divided by 3, that is 2 operations. If there were 5 elements, then upper bound of 5 divided by 3, that would be something 1.6 something, 1 point something, and that would also end up being 2. And if you needed to remove 7 elements, basically you, in this case 2, you would have to do 3 operations because like 1, 2, 3, 4, 5, 6, and 7th element. You can remove, do one operation, remove the first 3, do second operation, remove the second 3. And to remove this last element, you would have to do one more
train,
operation.
train, 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 train.
So that was about the first problem. If we move to the code part, and of course, if there are no duplicate elements in the complete array, you don't really need to do an operation. So in that case, you'd have 0 as your answer. So in for the code, first we take the size of array, and then you can maintain a visited array, or you could do it using sets or maps. In this case, since the constraints on number are like they are between 1 to 100, the best alternative would be to use a Boolean array. And so we iterate from right to left for from n minus 1 to 0. And we see, okay, is this element already visited? Have I already seen this element in the suffix that I have iterated up to? If I have, then I have to remove the first I plus 1 elements, because this element can't be the part of my final array. To do that, we'll need the prefix length, the seal of prefixes length divided by 3, that is 3 plus 2 divided by 3 number of operations, and we can just return these operations. Else, we just visit the current element and just go on iterating towards the left. And if there are no duplicate elements in the array, you can just return 0. 0 of lambda 3. Yeah, right. Now, let's move to the second problem.
Sir,
Okay. Yes,
uh,
is there?
sir, I have one issue, sir.
Yes.
Sir, can I begin with Hindi language? Is it comfortable for you?
Yeah, sure.
सर अगर इसमें तो सर 100 लेंथ थी, जैसे एरे की जो रेंज थी वैल्यू की नम की, अगर वो और ज्यादा बड़ी हो जाएगी तो क्या हम उतनी बड़ी एरे लेंगे वेक्टर?
Okay. So rather than taking like what you're trying to say is, okay, if my array of I is up to 10 power 9, something like that.
यस यस.
In that case, what you can do is you can have in C++, you can have a map from int to bool that now look like the current time complexity is big O of n, because each of these axes is like you're looking up an array. So each of these axes is big O of 1. So in C++, you can use a map from int to bool. That would look something like, rather than having this visited array, okay, sorry, this is second. Rather than having this, you can have a map from int to bool visited if the values are up to 10 raised to power 9. Even in that case, this would work. The only thing is that with maps, lookups are big O of log n, so your time complexity would increase to big O of n log n, because for each iteration, you are looking up one element, and for map, that takes log of n. Or you can use unordered map, and that would still work in big O of n, but it has more overheads and the chance of collision. Basically, you can use either map or unordered map in case the values are up to 10 power 9.
ओके, थैंक्स सर.
Okay, let's move to the second problem. So in the second problem, we are given an array of integers nums and an integer k, and we're allowed to perform the following operation. In each operation, and each operation can be performed on each element at most once. So in each operation, we are allowed to add an integer in the range minus k to plus k to the element, and we have to return what is the maximum possible number of distinct element in nums after performing this operation. So let's take the sample case, test case 1, 2, 2, 3, 3, 4, and the value of k is 2. For a sample 1, 2, 2, 3, 3, 4, and the value of k is 2. Now, value of k being 2 means that you can add any number in range minus 2 to 2 exactly once to each of these elements. Minus 2 to 2 means minus 2, minus 1, 0, 1, or 2. Okay. And the constraints on k were up to 10 power 9, nums of I is up to 10 power 9. So basically your nums length is up to 10 power 5, and k and nums of I are up to 10 power 9 and greater than equal to 1. actually k is greater than equal to 0. Now, if we look at this test case, and we were given k equal to 2. Okay, what you can do is in the first element, we can add -2. So after adding -2, this becomes -1. In the second element, once again, we can add -2. So 2 minus 2 becomes 0. In the third element, you can add -1. 2 minus 1 becomes 1. In the third element, we can add -1. 3 minus 1 becomes 2. Fourth element 0. 3 and 0 is 0. And fourth element, we can again add 0, which is, 4. 4 plus 0 is 4 minus 0 is 0. So we have 1, -1, 0, 1, 2, 3, and 4. We have exactly 6 distinct elements. All right. And we have to maximize these distinct elements. So let's consider the second test case for like a bit more clarity. In the second test case, you had 4, 4, 4, and 4, and you had k equal to 1, implies that you can add numbers in the range -1 to 1. So you could either add -1, 0, or 1. Okay. We have 4, 4, 4, and 4. For the first 4, let's just add -1. So 4 minus 1 is 3. For the second 4, let's keep it as it is. 4 minus 0 is 4. For the third 4, let's add 1. So 4 plus 1 is 5. And now for the fifth 4, no matter what you add, -1, 0, or 1, it would always end up being either 3, 4, and 5, 3, 4, or 5. And all of them have already been present in the array. So the thing is that in this case, you can only have at most 3 distinct elements. So the answer in this case is 3. Yeah. So those were the sample test cases. Let's move to the, okay, can you please try run for 7, 6, 7. Okay. So 7, 6, 7, 6, 7, and k equal to 1. All right. Let's just like write this in sorted order to make it easier. So k equal to 1 means that that you can add numbers in the range -1 to 1. That will be -1, 0, or 1. You want to increase your range as much as possible. So let's just reduce the first element as much as we can. So we'll just add -1 to 6. That will give us 5. Let's add 0 to 6. So that will give us 6. Then you can again add 0 to 7, because if you add -1, 6 is already visited and you want to maximize distinct elements. Then you can add 1 to 7. That would be 8. Now, no matter what you add to this 7, -1, 0, or 1, it will either be 6, 7, or 8, all of which are present in this first part of the array. So this you can add anything and it would be like 6, 7, and 8, and this won't contribute to the number of unique elements in the array. All right. Okay. So that was the dry run for that. And let's see what's the intuition that you can use to solve this problem. Okay. Consider this test case. So let's consider the test case 1, 2, 2, and 2 and 5. Okay. So let's just try to plot what a solution will look like. So 0 here, 1 over here, 2 over here, 3, 4, 5, and say a 6 over here. All right. Now the first element is 1, and let's just say that our k is 1. So to keep the test case within bounds, like easier to imagine, let's keep it within 1. So this is your first element. Up to where can this go? Well, this can go to 1 minus 1, 0, or 1 plus 1, 2. All right. Your second element is 2. This can go to 2 minus 1, 1, up to 2 plus 1, 3. Then again, your next element, next four elements, next three elements are 2 itself. So these would also lie in this range. So basically, you have 1, 1, 4 twos, and the final one is 5. All right. So 5 would lie somewhere over here. And 5 can go up to 5 minus 1, 4, or 5 plus 1, 6. Okay. Now, in the most optimal case, what we want to do is we want to maximize the number of unique elements. So let's take the smallest element and have its like lower bound. We will try to include its lower bound in this in our array. Why this? Because if you have an optimal answer starting over here where the minimum element is this and you have some elements above this, and you can always have an answer such that the minimum element is like below this guy. So let's start with this the minimum possible element, that is 0. Okay, now since this is minimum possible element, you can't have minus 1. The next unique element that you can have is 1. Let's see if 1 is possible. Well, we can see over here that 1 is possible over here. So we have 0, then we have the next possible unique element, that is 1. Okay, now 0 and 1 have been done. What about the next possible unique element? Well, 0, 1, and then we have 2. Is 2 possible? Yes, 2 is possible. So you have 0, 1, and 2. Now, what's the next possible unique element? That is 3. Is 3 possible? Yes. Then let's try to see for this. Like we have been assigning like 0, 1, 2, and 3. Now, for this element, it can take values in the range 1, 2, and 3. You see that since 3 is visited, like since the next possible element is 4, all the values that this element can take are not unique anymore. They have been visited previously. So basically, we just set this element to anything we want, or we can just set it to 3 for now. And the next possible unique element would be 4. Okay, so we look out for 4, and yeah, when we come over here at 5, we have 4 as our possible element. And then the next possible element would be 5, but we don't have any numbers left for uh, converting them to 5. So in this case, like the maximum number of unique elements would be like 1, 2, like 0, 1, 2, 3, and 4. So we would have 4 maximum possible unique elements. Basically, what the intuition is that you start at the lowest element. You first like kind of sort the elements. You start at the lowest element. Okay, you say that this is my first element, this is my smallest element. Then you go to the next smallest element, look at its range, and try to say, can I have the next element? That this is the element, what is the next element? This is the next element. Can I have it in this range? Can I have it in the range of this next smallest element? If you can, you basically cut it over there. Or it may happen that, for example, you are at 1 and this is 0 to 1, and you are at 3 and this is 2 to 4. Then let's just say that you visited 0 and the next element that you wanted was 1, but the next smallest element is 3. So you just had to skip 1 and you just had to go directly to 2. So the basically what you're doing is we start with the smallest element, then we go to the next smallest element and see what is the next unique element that I can assign in this range. So the next unique element would be the maximum of either what is the minimum element it can achieve over here, or the next element that I have assigned in this range. Okay. I don't think there are any doubts. All right. So that was the logic, and basically what we'll do with respect to our code is we'll first sort our nums array, and then for each element we'll assign the first element to say that if the first element is 1, we'll assign it to 1 minus k, whatever that is. Then for the next element, say it is 2, Okay. And let's just say that this 1 minus k is 0. We'll try to assign the next unique element. So if the smallest unique element is 0, the next unique element is going to be 1. So can I have 1 in this range? If I can, I'll have 1 in this range. If the next element was say greater than 1, like the lower bound was greater than 1, if this was somewhere in 3, then rather than having 1, we'll directly jump over to 3 and we'll go on assigning elements, so on and so forth. And let's just walk through the second test case for this. So this test case was basically 4, 4, 4, and I think your k was 1. K was 1. Basically, we had 4, and 4 minus 1 is 3, and 4 plus 1 is 5. And we had 4 such elements. Okay, all of them are equal. So first, we assign the smallest unique element, that is 3. Then we try to assign the next smallest. So 3 plus 1 is 4. The next smallest unique element would be 4. Then we try to assign the next smallest. Well, 4 plus 1 is 5. Can I assign it? Yes, I can. Then we try to assign the next smallest element. 5 plus 1 is 6, but we can't yet assign it over here. So we'll just assign whatever we can, that is 5. And over here, if we had one more element, we would still try to assign the next smallest unique element, that is 6, until like we are at the end of our array. Okay. So moving on to the code. So we first sort our nums array, then we take our smallest element and like decrease it as much as we can so that we have maximum degree of freedom. Then initially we say that, okay, all my elements are unique elements. So let's just say our res was n. Then we iterate from the second element. And since if we assume that the last element was the maximum unique element in our array up to now, I can increment my current element by at most k. So if nums plus k is still less than the next unique element that I want, then I just can't have it, and we'll just assign it to nums of I equal to nums of I minus 1, and this element is no longer a unique element. So we decrement our res. Otherwise, what we say is, what is the next unique element I want? That's nums of I minus 1 plus 1. And what is the minimum number up to which this element can go? That's nums of I minus k. So we'll assign the current element to be maximum of both of these things. Basically, what this line deals with is, if you have something of this form, say your k is 1 and your first element is 1, then it can go from 0 to 1, 0 to 2, and say you assigned your first element to 0. What happens if your next element jumps to 5? That can go from 4 to 6. Now you want your next element to be 1, but your 5 can go at most up to 4. So you say we'll assign our 5 to 4. And then our next element is say 6, then that would get assigned to 5, and so on and so forth. We can just continue. And this if statement, basically what this says is, over here in the four part, you assigned 3, you assigned 4, you assigned 5, and the next element you wanted was 6, but this 4 can only go up to 5. So we just say, okay, this is no longer any unique element, and we'll just assign it to 5 and try to assign the next elements to 6 and higher. That was the second problem. No doubts. So I think we can move to the third problem. Now, the third problem said that we are given a binary string s of length n and an integer numops. And we are allowed to perform the following operation on s at most numops times. In one operation, we select an index I and we flip s of I. Flipping s of I means if s of I is 1, then we convert it to 0. If it's 0, we convert it to 1. Basically flipping in a binary string. And what we needed to do was we had to minimize the length of longest substring of s, where all the character in the substring are identical. And we had to return this minimum length after performing at most these number of operations. And a substring is a continuous non-empty sequence of characters, basically a continuous substring. Let's take the first test case. So this was the first test case was, and also about the constraints. In this problem, the constraints were where the size of array is up to 10 raised power 3 greater than equal to 1, and the number of operations that we had was less than equal to n but greater than equal to 0. And the only difference between the third problem and the fourth problem is that in the fourth problem, the problem is completely same. It's just that in the fourth problem, the constraint are up to 10 power 5. The n value in problem D, you have n up to 10 raised to power 5. Everything else is same in. So let's take the first test case. So in this case, we have S is 1, 2, 3, 4, 5, and 1. 1, 2, 3, 4, 5, and 1. And we have num ops equal to 1. So we have one operation, we can flip any one of these characters. And what is the minimum length of the like longest substring which has all characters same? Now first we have this string. What is the longest substring with all characters same in this string right now? It's this, that is 5. So this has length of 5. We have 5 continuous zeros. So currently this string would have 5 as its value of the longest substring with all characters same. What we can do is we can flip. Okay, someone is drawing here. Okay, what we can do is we can just all right. Now what we can do is we can flip one of the bits. Let's just say we flip this bit, this character, then you would have 0, 0. After this flip, this would become 1, 0, 0, and 1. And in this case, like you have these two are same characters, so we have this one array of similar characters of 1, this one subarray of size 1, this one subarray of size 2, and this one subarray of size 1. So in this case, you would have like 2 is the length of the longest substring which has all characters same. Okay, and the answer would be 2 in this case. And so there are any doubts? Can you show the code for second problem once again? Okay, yeah. And for the second test case, like we have 0, 0, 0. So we have 4 zeros and we have 2 operations. Now we have 4 zeros and we want to minimize like the number of continuous, like number of substring with all characters same. What we can do is we can flip the second and last characters. So we can have 0, 1, 0, 1. And in this case, you will see that all basically blocks of same characters are of at most size 1. So our answer would be 1 in this case. So that was 1. And in the last case, test case, like we are given 0, 1, 0, 1 by default. And the answer would be 1 in that case, because in case of 0, 1, 0, 1, this is the most optimal subarray. Like you can't have an answer less than less than 1, because if you have at least one character, then that character would in and itself form a substring of length 1. So your answer would be at least greater than equal to 1, and this subarray has a value of 1. So even with 0 operations, the 1 would be answer, even if your operations were greater than 0. And those were the test cases. Now let's move to the intuition behind how you would solve the problem. Okay. Let's consider like k equal to 2. So first notice that rather than having to say, I am giving the number of operations and then find the min length. Okay. This would be a bit like difficult, like going from here to here is slightly difficult. Like how do you know, like from the number of operations, how do I find the minimum length? An easier problem to solve would be, I want, like, sorry, I want the maximum subarray with same characters to be have length x. So I want this x to be the value of my string. Then what is the minimum number of operations I need? Like you can kind of see why we can solve this kind of problem. Like basically we can try to break it into subarrays or something, but this would be like very difficult to solve. Like I have these many operations and directly how do I know that what is the minimum length of the subarray, the maximum subarray with all characters same. So this would be an easier problem to solve. But now on the based on this, how do I derive what is the maximum length I can have? Now consider one thing. Let's just say we had this 0, 0, 0, and our number of operations was 2, right? In one operation, you can have 0, 1, 0, 0, or you could have 1, 0, 0, or you could have 1, 0, 0, 1, 0, or something like that. This has a value of 2 because you have two a subarray of size 2 with same characters. This has a value of 3 and this has a value of 2. And after two operations, you could have 0, 1, 0, 1. And this has a value of 1. Now, in two operations, you can achieve, like in at most two operations, you can achieve a value of 1. In two operations, you can achieve a value of 1. That also implies that to achieve a value of 2, like basically to get the answer up to 1, you can also like basically modify the operations a bit or do some less operations to get your value up to 2. So basically what we are saying is, if I can reach up to 1, then I can definitely reach up to 2 using two operations. Then I can also definitely reach up to 3 and so on and so forth. Like if it's possible to convert the array to have value of 1, then you can definitely convert it to have a value of at most 2, at most 3, and all of them. All the way up to n, because you can't have an array with a subarray length greater than n. So that's it. Basically, what I'm suggesting is we can binary search on this x. So let's just say we define this. What's the min ops of sx? What this says is, what's the min number of operations that you need to make like the max same substring in S to be to have length x. So what this says is, what is the minimum number of operations that you need to perform on S such that your value of S, that is the maximum length of substring with all characters same, will be x or less than x. Now if you can make it so that the minimum number of operations that you need to make the value of s equal to 3, say it's 10, then for 4, it will be 10 or less than 10. It will be 10 or it will be 10 or 9 or something less than 10. It can't be greater than 10, because if you need greater than 10 operations to just make your value up to 4, then to make it up to 3, you will need more operations, because in each operation, you're actually reducing your value of string. In each operation, if you look at your 0, 0 graph, here the value of your string was 4. When you did this, the value of your string became 2, these two, and this complete 4. And when you did the final operation, the value of your string became 1. Now, in an intuitive sense, what you're doing is, after each operation, the value of your string is actually decreasing. So if the value of your string is decreasing, then to get to 3, you'll need more number of operations than to get to 4. Not exactly 4, but at most 4. Like the value of your string is at most 4. Exactly 4 would be a difficult thing, but at most 4. What we can do is we can just binary search on our values. Let's just say that initially 1 to n is all the possible set of values that we are holding. Then we can just have some mid element, and we'll check what's the number of operations that I need to get to this mid element. Say that the number of ops that I have is 10. If I need 11 operations to get to this element, then to get to 3, then to get to 2, to get to 1, I'll need at least 11 operations or maybe even greater than that. So if I cannot make my string reach mid, then I can definitely not make them reach 1 to 3. So my answer would lie in this range mid plus 1 to n. And we can just go on binary searching on this and reduce our range into halves in each iteration. So that was the binary search part. Now the next part is how do we implement this minops function? Are there any doubts? Yeah, binary search can be used. Continuous divide into length plus 2 bit continuous. Okay. Now the question is how can we binary search this thing? Sorry, not how do we implement this thing? Like what's the minimum number of operations to have like I'll just say over here value of s equal to s. This value basically means that the maximum substring with all characters same, maximum length of substring with all characters same. Well, how do we implement this function? Once we can implement this function, we can just insert it into our binary search and get our answer. Now the question is how do we implement this function? Let's just say that consider a test case like the value of our x is 2 and say that our s is zeros, all zeros. Okay, like this is the simplest possible string. If you have 0, then it becomes slightly more complicated. Let's consider that all our characters are same for now and we have value of our x equal to 2. Okay, so I consider the first character. Is it valid? Yes, I mean, this is just one substring of length 1. Is this valid? Yes, this is valid still because this is just a substring of length 2. When we try to add the third character, that is 0, this would no longer be valid. This would create, if we add 0 as it is, this would create a substring of length 3 with all characters same, and that would violate what we want, that our value should be 2. So what we can do is, after adding the first 0 zeros, we can add another 1 when adding the third character. And then we try to add the next character, 0, which is like fine. Now, let's try to generalize what this looks like. Let's just say that you have a string of any length, say n, and your value of x is, let's fix it for now. The value of x is 2 for now. Okay. What are you doing? You add 2 zeros, and for the third 0, you convert it to 1. You add 2 zeros for the third 0, you convert it to 1. You add 2 zeros for the third 0, you add it to 1. You can see that this is the most optimal way to do it because in any condition you would have pockets of two zeros and ones in between. And you add 2 zeros and add the like third 0, convert the third 0 into 1. And at the end, you can have either no zeros or 1 or 2 zeros. So basically, if you look at it, what you're doing is for every subarray of length 3, you're kind of keeping 2 zeros same and converting 1 0 to 1, keeping 2 zeros same, converting 1 0 to 1, keeping 2 zeros same, converting 1 0 to 1. And if you really like want to generalize what this is, so this had, I guess, 12 plus 2, 14. So in how many like 3 0 pockets do you have in this string? Well, that's just 14 divided by 3. Like 14 divided by 3 is 4. 4 3s are 12. This would be like 4.6 something, and the lower bound would be 4. So basically, if you have any subarray of length n, and all of it is zeros, and you want to convert it to have value of 2, you just do this operation, like keep 2 zeros, convert the third into 1, and you do it as many times as you have this substrings of length 3, and there would be n divided by 3 of these things. So if your S is all zeros, if your X is 2, then your answer would be like this min-ops would be n divided by 3, the lower bound of it. Now you can also generalize it to have to any X. So even if X is 4 or 5 or 6 or 7, anything, and if S is all zeros, we are just considering all zeros up to now, and it has length n. What you're basically doing is keep the first 4 or first X zeros as it is and convert the X plus 1th zero into 1. This is the X plus 1th. So you basically need blocks of size X plus 1. And how many such blocks can you have in an array of length n? Well, in an array of length n, you will have n divided by X plus 1 such blocks. So if your S is all zeros, or in fact even all ones, if all characters in S are same and S has length of n, then your min ops of S and X will basically be n divided by X plus 1 and the lower bound of it. Any doubts? Please. Explanation of question. Okay, so in the binary search part, basically what we are saying is, we're trying to use this function like what is the minimum number of operations that I need to make the value of S equal to this X, and what our observation is that if you need 10 operations to make the value equal to at most 3, then to make the value at most 2, you will at least need 10 operations. So basically what we are seeing is that in every operation, the value of a string is decreasing. So over here it was 4, over here it's 2, and finally over here it's 1. So after each operation, the value of our string is decreasing. So if you can make your string to have a value of say 2 using 10 operations, then you can definitely make your string to have a value of 3 using 10 or less than 10 operations. Okay. So based on that, we can just binary search, like we can maintain our initial range from 1 to n, have this mid. Do I need 11? What's the number of operations do I need to have make our value of string equal to mid? If it's 11, if it's greater than 1, 2, 3, all the way up to mid, all will take at least these many operations. So they aren't a part of answer, and we can search from mid plus 1 to n. And based on that, we'll just binary search. About the minops, so like for now, we have an answer. If all the characters in our string are same, if all the characters are same, there are n characters, and if our X is this thing, we basically go on dividing it into blocks of size X plus 1, and our answer would be n divided by X plus 1. And this all is for like X, say greater than equal to 2. For 1, there would be a slight complication when we try to generalize, so we'll deal with that separately. Now, this was when S was all characters same. Okay. Now consider what happens when S can have different types of characters. S can be 0, 0, 0, 1, 1, 1, and say 4 zeros over here. Let's explain the predicate function again. Okay. The predicate function. Okay, like this predicate, if you're saying about minops, basically what minops is saying is that you have this string S, and I want X to have this value of X. Like I want the maximum subarray with all same characters to have value of X. What is the minimum number of operations that I need to make S to have value of X? So for example, if you had like, let's just say over here, yeah, right. So for example, if you had this subarray like 0, 0, 0, 0, 0, 14 zeros, and you wanted it to have a value of say 2, like the maximum subarray with all characters same should have value of 2, then you'd keep the first 2, convert the next 0 to 1, keep the next 2, convert the next 0 to 1, and so on and so forth. And the minimum number of operations that you would need is basically you have converted these 4 zeros, like flipped these 4 zeros. So the minimum number of operations would be 4 in this case. And we are just checking if the minimum number of operations, like do we have these many operations? If we have, then this is like this can be our answer, and we'll change our range according to our binary search. So yeah, that was the predicate function. Okay. Now we have how would we implement our function for all characters same in the array? Now the question is, what happens when we have a general case where we could have 0 0 1 1 then again 0 zeros? Well, the basic idea would be try to divide it into blocks. So we have an answer where all characters we have an answer if all characters are same. Then what we can try to do is we can try to divide it into blocks. Okay, so take the first block. This is all zeros. Okay, and say that the value of our x is 2. Now, according to our previous logic, what would be the answer in this case? Well, this has a length of 3, and 3 divided by 2 plus 1 is 3. So the lower bound of this would be 1. So you would need exactly one operation. Okay, you have 0 0 1. Basically, this would correspond to converting it 0 0 0 to 0 0 1. Now, this poses a slight challenge because you have 1 1 1 over here. Okay, and if you convert it to this one, like this can combine with this one to basically change your block sizes. But now, if you actually look at the operations that we are doing, if you do one operation, you're converting one like 0 into 1, and you have at least two zeros if your x is greater than equal to 2. So that's why we'll deal with the x equal to 1 case separately. If your x is greater than equal to 2, then you have at least two zeros behind this one. What you can do is you start with zeros. Definitely you start with zeros, and at the end, if you have a 1, then you have at least two zeros behind this one. What you can do is we can just swap this, like rather than converting this 0 to 1, what we can do is we can convert this 0 to 1. This would still maintain our condition because basically this has a size of 2 and this has size of 1 and this has size of 1. What I'm trying to say is you can do your operations in such a way that if you have this 0 0 0 0 block, after performing all the operations, the starting and the ending bits are both zeros, and you have some ones in between. And the number of operations would still be like n divided by 3 or n divided by x plus 1. So you could just do your operations in such a way, and that would keep all the blocks isolated from each other. And if that's the case, then what you can do is just operate on all the blocks separately. Okay. We can take this. This takes 3 divided by our x equal to 2. So our x plus 1 would be 3. So this has length of 3. So 3 divided by 3 is 1. And basically this would correspond to converting it to 0 1 0. This again has a length of 3. 3 divided by 3 would be 1 again. That would correspond to convert it into 1 0 1. We are flipping the middle bit. And this has a length of 4. 4 divided by 3 is 1, like 1 point something, and the lower bound of that would be 1 again. And we can just say that first two and the last 0 0 1. And since we have one more 0, we don't really need to put this in between or anything. And yeah, like what we can do now is we can basically break our array into these blocks, say B1, B2, and B3. And to make each block valid, you would need B1 divided by x plus 1 operations. To make the second block valid, you would need B2 divided by x plus 1 operations. And your min ops would be sum of all these blocks. And that's how we can deal with our operations if x is greater than equal to. And what happens when x is equal to 1? Well, x equal to 1 is a bit problematic because when we were dealing with this thing like 1 0 0 1 and once after this thing, we assumed that we had at least two zeros behind this one and we can just flip it. So you could also have like once before this and once after this. So if you consider a test case like this with x equal to 2, then you could have, like, if you just try to assign this to 1 0 0 or 0 0 1, then this one would merge with the previous block and create a block of size 3, and that would violate our answer and even over here. So for this, we assume that we had at least two zeros over here, and we can just swap this one to cover it with zeros, and that would preserve our like boundary of our blocks, and we would be fine. Now with x equal to 1, we have a problem that you can have something of this form. 0, 0, 1. And no matter what you do, like 1, 0 or 0, 1, well, by definition of our main ops, if we just ran it with x equal to 1, this is a block of size 2, so this would take 2 divided by 2, 1 operation. But no matter how you do this operation, 0, 1 or 1, 0, you would always end up with an array of this form. So our min-ops logic doesn't work when you're x equal to 1, because you could have like you don't have two zeros that you can use to pad your bit change. And in this case, it may happen that the flipped bit may merge with the previous or next block. But so you have to deal with x equal to 1 differently. So you have to deal with your x equal to 1 case differently. Now, notice one thing, when you're x equal to 1, what you're saying. Okay, so x equal to 1 can actually be a very simple case. If x equal to 1, if this character is 0, this already forms a substring of length 1. I can't have the next character as 0 because that would create a substring of length 2. So if this character is 0, then, sorry, I'll just draw it later. Okay, if this character is 0, the next character has to be compulsorily 1. Now this character is 1, next character has to be compulsorily 0, 1, 0, 1, 0, 1, and so on and so forth. If my first character was 1, that would be 1, 0, 1, 0, 1, 0. And in case of x equal to 1, you basically have only these two options. Like if your initial substring is this, then for x equal to 1, you only have two options. Either this 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, or this 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. What we can do is we can just check if we just compare these two strings, and wherever they differ, like it differs over here, it differs over here, and it differs over here, differs over here. Wherever they differ, we flip our bit. So we will need 1, 2, 3, and 4 operations. And similarly with this guy. So wherever they differ, we flip our bits. And after flipping your bits, we'll need 4 operations, like 4 flips to convert this array to 0, 0, 0. And we'll need, I guess, 1, 3, 4, 5, 6, and 10, like 6 operations to convert this string to 1, 0, 1, 0, 1, 0. So we can just deal with the one case separately, and we'll see like the minimum of 4 and 6 will need 4 operations to make the value of our s equal to 1. And we can just check if 4 is less than equal to min ops, then our answer is 1, because we want to minimize the value of our s. If it's not, then we can just binary search starting from l equal to 2 and r equal to n. And yeah, I mean, in binary search, like the usual binary search, we take the mid, we check the min ops for it. Like, are the minimum operations for this thing, if the minimum operations for this thing, if I can perform those many operations, then my answer would be at most this. If I can't, then our answer will be greater than this. So this would be your usual binary search. And also the time complexity for this, like what we are doing is we are dividing our entire string into blocks that would take big O of n time. And we are basically doing some arithmetic operation on each of blocks. So that would overall take n time, big O of n time for minops. And for the minuses, that would take big O of log n time, because our range is from 1 to n. For space complexity, depends on how you implement it. For my implementation, it would be big O of n. You could have better implementations where space complexity could be reduced to big O of 1. Okay. How did this strike your mind? I couldn't think of handling x equal to 1 separately. Well, you could actually, means the moment you say thing about flipping your bits, so you should consider the edge cases. Now, when you're considering edge cases, like if a thing that you need to consider when you're flipping the bits, you're dividing your string into blocks, and you want to preserve these blocks. So when you flip, there's a chance that these blocks won't be preserved. And the basic idea is, how do you preserve these blocks? If you can't preserve these blocks, then the whole thing about the whole derivation of the minops function becomes useless, because you don't really have the blocks that you assumed you had. So the question is, how do you preserve these blocks? Now, you could just go through a bit of trial and error and see that for x greater than equal to 2, you can always preserve these blocks, because for every one, you have at least two zeros before that one. And we are basically assigning ones start, like the first element would definitely be 0. The second element would definitely be 0 for x greater than equal to 2. And we can just go so on and so forth. And the last element, if it's 1, you will have at least two zeros before this one. You can just kind of swap these and you can preserve this. But in case of 1, well, maybe it's possible, I don't know, but as far as I have tried, you'd always like have a problem with in case of 1. Like this is one of the cases, and you can also try out a few cases and see if it fits. But basically, in case of 1, you will always have this problem that even if you deal with one block, converting into 1 0 or 0 1, it will always have this problem that this block, the very definition of your block, that it started and ended with 0, is not preserved. You can't preserve that definition over here, and that would lead to problems. So since this is just one test case, you can just deal with it separately. Okay. All right. And if there are no more doubts, we can just move to the code. All right. Now moving on to the code for this problem. The first thing we do is we deal with the one case separately. We take our S, we take the size of S, deal with the one case separately. If the minimum number of moves that you need to convert S with to value of 1 is less than equal to the number of operations you have, then your answer is 1. You want to minimize your value. And how do we deal with that? Let's just say that res0 is starting with 0 and 0 1, and res1 is for converting your string to 1 0 1 0. And if you're converting it to 0 and 0 1, basically on all even indices you are placing a 0, on all odd indices you are placing a 1. So yeah, like if the index is odd, in case of 0 and 0 1, you need a 1 over there. In case of, yeah, in one of the cases you need 1 over here, in one of the cases you need 0 over here. If your index is even, then it would be reverse. In the case, in case of res0, you'll need 1 over here. In case you'll need 0 over here. So that was the logic for this converting into size of 1. And we just return the minimum of these, like the minimum number of operations you need to convert either to 0 and 0 or 1 0 1 0, minimum of those two. And if you can convert it to 1, then okay. If not, your answer would be at least 2 and at max n, because the size of your string is n. Then we just binary search. We take the mid, like L plus R divided by 2, and see what is the minimum number of moves that I need to make the value of my S equal to mid. If it's greater than this, then obviously for all values smaller than mid, the number of moves would be greater than numops. So the answer is going to be at least mid plus 1. If it's less than equal to numops, then we can at least have a value of mid. In that case, your answer would be mid or less than mid. So we can have R equal to mid. Basically, we are halving our range over here. Then how do we implement this min moves? Well, in my implementation, what I've done is I've just converted, basically broken down our array into blocks and maintained an array of blocks. So we are just doing something like, if maintain the current character. If the current character is equal, then increment the length. If it's not equal, then this is the end of the previous block. Push it into blocks. Update your current character and start a new block with length of 1. That is the current character. And finally, just push the current length into blocks, indicating the end of the last blocks. And this is the rest, and basically just what we discussed, like the block size divided by x plus 1. Over here, x is the max length. And finally, we just return our rest, that is the minimum number of operations you will need to make this whole thing work. And yeah, like rather than having this vector of int blocks, what you can do is just operate with length over here. That would be like better on the space complexity side of things. So that could do your space complexity to big of 1. But I thought that would be a bit difficult to understand, so it this way. So this was the third and also the fourth problem. So this works in a time complexity of big of n log n. So this would also work for n up to 10 raised to power 5. And the space complexity would be big of n or big of 1, depending on how you implement this thing. So this would work for both the problems. So the third problem and the fourth problem were actually same. So this was up to 10 power 3 and this was up to 10 raised power 5, the length n. Now actually there's one more way to solve the third problem. So that's using dynamic programming. Like this is kind of suboptimal in this case, but if it's possible, let's just discuss it just to be like for the completeness. So in the third problem, we had n up to 10 raised power 3. So what you could do is like, are there any doubts for the third and fourth combined, like the optimal solution? Okay. If there's anything, do put it in the chat. Like, so for the third problem, you actually had n up to 10 raised power 3. And we can have a solution that's n squared log n in this case. So the overall logic remains the same, just that how you implement your min-ops function, like the min-ops of s of x. Over here, we had this observation of converting it into blocks and then dealing with each block separately. That was our intuition or for the optimal solution. Now, there's one more way to solve this for n up to 10 power 3 using dynamic programming. And in this case, what you say is, okay, so I can do like I can have at more like a subarray of same characters with at most length x. Okay, so we have this 0, 0, 0, and what I can have over here is I can have this 0 or I can flip this and I can get 1. What are the different options that I have over here? I can get up to here like 0, 0 or 1, 0, or I can flip this character to convert it to 0, 1 or 1, 1. Okay. Do I really need this one guy? Like, do I really need what this one is or what this 0 is? Okay, I do need these things because if I add one more one, then this would violate my, say, let's just consider we are solving for x equal to 2. If I add one more one, this would violate my x equal to 2 condition. If I add one more 0, this would violate my x equal to 2 condition. But if my string is 0, 1, 0 or 0, 1, basically what we need is the size of the last block. Once this is done, like once this one is done, I can just forget this thing. Once this 0 is done, I can just forget this thing. What we need is the size of the last block, whether it's 0 or 1. What is the size of the last block? And what is the like character in that last block? Also, like this solution would kind of be suboptimal with respect to our actual solution, that is n log n. So this would only work for C, but this is also slightly more complicated than that. So what we are saying over here is what we want to maintain is what we are trying to say is what is the most straightforward dynamic programming solution that you can get. And what I'm trying to say is if you have done some number of operations up to this point and you are adding this another 0 into this thing, what you really want is even if you have something like 1, 0, 0, 1, 1, 1, 0, 0, 0, you don't really need to consider this array. You only need to consider this last part of your array, that is this block. What is the character? The character is 0. What is its length? The length is 3. If you add one more 0, the length would become 4 and the character would remain 0. If you add like a 1, your length would become equal to 1 and your character would become 1. Like basically, you're gonna either convert 0, 0, 0 by adding an 0 to it to 4 zeros, or adding an 1 to it into 3 zeros followed by a 1, and these zeros no longer became like you don't really need to consider these zeros anymore because any character that comes after 1 will be attached to this one and won't be part of this block. Okay. Now, once you have this observation, this will kind of point you to say, what are the two most important things of my last block? Well, the two most important things of my last block are what is the length of the block and what is the character of the block. And this will basically allow us to update this block. If I add a character of the same block, let's just say that we have a block with length of b and a character of 0. If you add a 0 to this block, this will lead to a block with length of b plus 1 and a character of 0. If you add a 1 to this block, this would lead to a block with length of 1 and a character of 1. And vice versa, like you could have b1 and that could go to b plus 1 1 or 1 0. 1 implies the length and 0 implies the character. What is the character that is present in your block? And what we can do is we can just try to see like what are the different possible states. Like I have my max length equal to x. So the maximum size of block in any valid array would be at most x. And say it start from 0, like 0, it's an abstract thing, but let's just say it start from 1, 2, 3, 4, 5, 6, all the way up to x. So I can have a block of size at most x, and I can have a character equal to 0 or 1. In this case, we can just define our DP state to be say 1, 0, 1, 1. Then like you can have a block of size 1, character 0, block of size 1, character 1, block of size 2, character 0, block of size 2, character 1, and so on and so forth up to block of size x, character 0, block of size x, character 1. So what we can do is we can say that for like DP of B0 is like the minimum number of operations to get and also like you also need to consider an I, like up to I for this prefix I. Minimum number of operations you need to get the final block of zeros, and it has a size of b. And let's just say that b can be between 1 to x. It can't exceed x because we are having calculating the function for min ops of x. Then what would this b of 0 depend on? Well, to get to b of 0, if your b is greater than equal to 2, you will compulsory come to b from b minus 1. And similarly for 1. So for example, to get like to 0 0 and whatever the rest of array can be, you first need to have an array of length 1. So you first need to have an array of length 1, and then you can go from 1 to 2. So for b greater than equal to 2, you will compulsorily depend on b minus 1 0. But if your b is equal to 1, what you do is you have like you want to start an block starting with zeros, and previously you would have a block of all ones. If you had a block of zeros, then this would lead to a block of size 2, so that won't be the case. What we want to calculate is the DP value for b equal to 1. In this case, what you would have is, okay, I have these ones, and now starting from here, I'll start with 0. And basically like we are doing a conversion over here from a ones block to a zeros block. So like that's kind of the overall idea, that we'd have a DP state of the block length and the block character, and we'll update this step for all like I from 0 to n minus 1. Like what is the minimum number of operations that we need to get this block length and this block character for the final block. And finally, like we can just iterate over all our DP states and see which one is a good one. And the transitions would be like for b greater than equal to 1, like instead of having this thing, what you can do is for b greater than equal to 1, you can say that for this block and for this character, this would like strictly depend on uh, the b minus 1 and this character plus something that you need to make the ith character equal to this 0. Basically, this corresponds to you want to have a block of size 3. Then what is the minimum number of operations you need to get to this block and any previous array? and what is like this corresponds to what is the number of operations that you need to get this 0. Like if this is 1, you need to flip. In that case, that would be 1. Or if this is a 0, then you don't really need to do anything and you just get a 0. So that would be one thing. And like rather than having 1, what we can have is say consider a block size of 0. And that would basically correspond to that you can start putting zeros from over here. Like the last element is 1. And what is the minimum number of operations that you need to clear the field to start filling zeros from over here. And what we can say is like for 0 0, you can work out these transitions. They are like slightly complicated to explain, but yes, I mean this would basically be like any block size greater than equal to 1, and you have like all ones filled up to here, and you need these many operations to fill up to fill with ones, and then you could just start filling zeros after this thing. So that would basically correspond to a block of size 0 with character 0. And if I were to show, could you question? Yeah, I'll share the codes. So like let's just move to code and see like how this is implemented. For the main length function, like the binary search remains the same. Only in this case, we don't really need to deal with the one case separately. Now, what we say is initially, okay, for all lengths and for all characters, our answer is n. Like n is the maximum number of flips you would do in any case, because in that case, you're flipping every character. Initially, let's just say that a block of size 0 starts, you need 0 operations to start a block of size 0. Then you'll iterate over all the characters, and for each character, we'll update all our DP states. Okay. For any block size greater than equal to 1, and we are iterating from right to left so that we can just do all this in n place. What we say is to have a block of length I and character j, we need to have a block of length I minus 1 and character j up to the previous character. And I need my current character to be equal to j. If it's not equal, we'll do a flip. So that would add an additional number of operations. Okay. Then the next, what we say is, next we update like dp of 0 0 basically means what is the minimum number of operations that we need to have a block of size 0. A block of size 0 means that a block of size 1 ends over here. So if a block of size 1 ends over here, this means that I can start a block with all zeros starting from over here. And basically, this is just an abstract way to deal with this. If you have this like the minimum, the operations that you need to make this string, like this block of ones, then you can just say that this is equal to the operations that you need to start a block of 0. And then like kind of your overall from 1 to max length would fit in this equation. So for 0, what we say is, okay, for any like set it to infinite, that is n, the max number of operations that you could have in this case. Then for each of the lengths from I to max length and for each of the characters, we say that dp of 0j to start a block of length 0 is like the number of operations I need is minimum of what I already need, or dp of I1 minus j, like what is the length of what is the number of operations that I need to have for a block of other character to end over here. Basically, what we are saying over here is, say, let's take a test case, say x equal to 1, because that would be like simpler. And say you have 0 0. And initially, like 0 0 and 1 0 would have values of 0, and 1 0 and sorry. So say this is your length and this is your character. So initially for length 0, character 0, you would have a value of like you would need 0 operations. For length 0, character 1, you would need 0 operations. For length 0, for length 1, character 0, you would need infinite operations. We are setting it to n, but technically infinite. In the first case, what we say is, okay, I have this 0. Now I can have what is the number of operations that I need to create a block with length of 1 and a character of 0? Well, that's what's the minimum number of operations that I need to have a block with length of 0, and I add 1 0 to this thing, and I'll get a length of 1 and character remains 0. So in that case, that would be like our first character is 0, so we don't really need to perform any extra operations, and the value of this DP is 0. So this would be updated to 0, sorry, 1 0. Like this would be updated to 0 and this would be updated to 1 because this would depend on this, but like 0, and you'd need to do +1 because you need a 1 over here, so you would have to do 1 flip, and that would be 1. And now when updating the length of 0 with character 0 and 1, what we are saying is, okay, I have this 0 or 1 over here, and what is the minimum number of operations that I need such that I can start a block of length, say 1, with character 0 0 over starting from this element. So if I need to start a block with length 1 from this element, then I need to have a block of 1 characters that ends over here. So basically, to start a block of length 1, I need to end a block of character 1. And to do that, what we just say is this length 0 for character 0, it's basically minimum of all the lengths with character 1, or in this case, it's 1. And for 0, it's sorry, for 0, it's 1, and for 1, it's 0. So this is 0. Basically, what it's saying is I can have 0 operations and this string 0. I can have 1 operation and this string 1. Okay. Now this string 0 also means that I can start a block of size 1 starting from the next element. And basically this means that using 0 operations, this is as good as saying that I have a block of size 0 with character 1 at this position. And similarly for this one guy, basically this means that what is the like what is the minimum number of operations that I need to have a block of size 1 end over here, and then I can start a block of block with characters 0 starting from over here. That is the basic idea over here, and that's how we would update the 0 part. And yeah, right, like finally we just take res equal to n. N is the maximum number of operations that you would do, because in that case you're flipping all the bits, and then we can just have iterate from 0 to max length and iterate over all the characters, basically all the DP states, and finally just take the minimum of them, and that would be our result. And the binary search remains same, like there's no change in binary search. Okay, all right. So yeah, those were the 4 problems, and this code only works for the third problem because this DP part, if you actually see, we have n into like x into 2 states. We have 2x states, or actually 2x plus 1 states. So basically we have big O of x time complexity, and we have big O of x space complexity for each of the minops function. And since like x can be up to n, your overall time complexity, sorry, the time complexity would be big O of x into n, because like we are iterating over the complete DP array for n iterations for each character. And the space complexity would be big O of x because we have this DP array. So the overall time complexity would be, since x can be up to n, the overall time complexity would be big O of n squared log n, and the overall space complexity would be somewhere near big O of n. So that was the last problem, and this would only work for C. So this was the C problem. And the solution of the D problem, the one using blocks, that will work for both of these. It's just that this is kind of like a more powerful solution. The time complexity is kind of suboptimal, but even in case that we had some slightly more complicated operations, this may have been helpful. But in this case, like we have this observation that you can deal with each block separately, and that allows us to have this big of n log n solution. So Yeah, those were the 4 problems for this Leetcode Weekly 429. Thank you for attending the PCD, and yeah.